Okay. So this is where we had stopped. We had said that when you do optical spectroscopy, there's 1D spectroscopy, 2D spectroscopy, and 3D spectroscopy. In a radio telescope, you usually do 3D spectroscopy, because that the spectroscopy part comes for free in the radio, because you split the signal into various channels, and therefore you get some kind of frequency resolution automatically. Okay. So how do you do 3D spectroscopy? So 3D spectroscopy is a technique which is becoming increasingly popular. And it's very useful because,
Yeah, did you actually share the screen? But I can't see, so that's why.
Okay. Thank you for catching me on that. Yeah, now you can see it, right? So then for the benefit of those who are there, so this is the spreadsheet that was shared by Prathamesh with me a few days ago. And this contains names of people and the corresponding paper that they've chosen. So just please verify that your name is listed correctly against your paper. I'm going to also put that on the web page, hopefully today. I've been quite busy with the ASI meeting, so things are getting a little bit delayed, but I'll do it today now that that meeting is over. And that's it. So I will discuss maybe next time when we can have the seminars. I would positively like to have the seminars during the week of 25th April. So we'll try and fix a date, mutually convenient date next time. And hopefully if we choose a date first, then the other exams, etc., can be worked around that date. Okay, so this is where we were. So when you want to do 3D spectroscopy in the optical, it's a bit tricky, because what you have to do is you have to take the light out from every pixel or every group of pixels in your optical image, and funnel that into a spectrograph and image it. So one of the early techniques that was used for this kind of spectroscopy was using what is called as a lenslet or array, or a lens array. And the idea is simple. There, at the focal plane, you actually place a filter, of course, an enlarger, and an array of lenses. So you have 1 lens, 2 lens, 3 lens, all arranged in a sort of a grid. And whatever goes through one lens produces one spectrum. And whatever goes through the adjacent lens will produce, whatever light goes through that will produce another spectrum, and so on. So the grism here is the dispersing element, and eventually it goes into some lenses again, and eventually your charge coupled device, which is your imaging detector. And this Sauron came online about 20 years back, and for many years it was the only integral field spectrograph in use. Then, of course, some other spectrographs came up, and then in the last 5 or 6 years, integral field spectroscopy has really taken off, because there have been 3 large surveys of galaxies using dedicated integral field spectrographs. One is a survey called Khalifa, and then there is another survey called SAMI, SAMI, and then there is a third survey which is part of the Sloan Digital Sky survey called MANGA. MANGA stands for Mapping Nearby Galaxies at APO, and these 3 surveys taken together have mapped, I think, of the order of 20,000 galaxies. And MANGA itself has mapped more than 10,000 galaxies. And now this kind of survey is very important. Integral field spectroscopy is very important, because in one go it gives you everything. It gives you photometry in one go. It gives you the chemical composition of in one go. And the chemical composition is both the metallicity of the stars as well as the gas phase metallicity. It also gives you simultaneously the kinematics of the entire galaxy, all the components. In the central region, you can study the kinematics of the bulge. In the outer regions, you can study the kinematics of the disk, and so on. And you can do separately again for stars by using appropriate lines. You can study the kinematics of the gas and the kinematics of the stars separately. So for studies of galaxy evolution, this kind of complete picture is very useful. So this is like taking an MRI of your body where everything is seen clearly. This is resembles that because it gives you all the information that you want in one go. Of course, these things are only possible for nearby galaxies, but for nearby galaxies, they really have revolutionized our knowledge of galaxy evolution. So this is what an IFU spectrum looks like. So the X and the Y are, of course, the coordinates of the galaxy, right? Ascension, declination, if you want. And what is shown in the various colors are the velocities. So this is a velocity map of the galaxy. Okay. And what kind of galaxy do you think this is? Is it elliptical or is it a spiral, or why do you think it's elliptical? No, this is not a jet. These are velocities only. So the color represents velocities.
I think it's a spiral because
yes, it's a spiral. That's right.
One part is moving
because
towards and the other
it's
is
clearly rotating, right? And normally when these kind of maps are presented, the convention, the sensible convention is followed, which is red color usually represents redshift, and blue color represents blue shift, and intermediate colors represent intermediate values. So clearly this is a rotating galaxy.
Sir,
Yeah.
what are these contours like, these lines?
The lines are the optical, I mean the photometric contours. Okay. And what is shown in the color are the velocity contours. Okay, or the velocity map. So there is a galaxy which is sort of elliptical, looks like an elliptical, but that's probably just the disk of the galaxy. And what you're seeing is rotation, clear evidence of rotation, wherein you have this red part is receding away from you, blue part is coming towards you. So you know the sense of the rotation. Right. So nowadays with integral field spectrographs, but also earlier with the long slit spectrographs, we were able to measure the rotation of various spiral galaxies. We saw that last time that was what helped in the discovery of dark matter in galaxies. But studies have also revealed that the nature of the rotation curve seems to, for a given morphology like spiral galaxy, seems to depend on the luminosity of the galaxy. So if the luminosity is high, the rotation amplitude increases and the initial rise becomes steeper. However, the outer slope drops. Okay, so there seems to be, so what is shown here on this axis here is the absolute magnitude of the galaxy in question. So we are going from minus 18.5 to minus 23.2 absolute magnitude. This of course is the more luminous galaxy. And as you can see that the rotation amplitude is higher, it reaches to higher velocities. But as you go outside, the outer slope drops. Okay. Now remember, these are all spiral galaxies, but in the inner region, they do have contributions from the bulge as well. So you have to keep that in mind. So for luminous early type spirals, the VR rises rapidly because the bulge is more important. And for low luminosity later type spiral, VR rises more slowly, and often VR can be proportional to R. Okay, not obviously not over a large extent of R, but in the central regions, okay, in the central regions, we do see spiral galaxies often showing what is called solid body rotation, where the velocity of rotation is proportional to R. The angular velocity is constant. So this we already looked at last time in the hypothetical situation where the supermassive black hole at the center contained most of the mass of the galaxy and there was no dark matter. How would VR look? Keplerian, but starting from the center. So you would have the highest velocity, you won't have zero velocity at the center. Close to the center, you will have a very high velocity and it will drop off as 1 over root r as you go to higher radii. Okay, so now these objects are moving. Let us say they are in circular orbits in the disk of a spiral galaxy. Let us say that all stars are in a circular orbit around the center. How can we use this to measure the mass of the galaxy? Sorry? mv square over r, correct. So what you do is that first of all, you have to assume that the velocities are more or less circular. This is a reasonable assumption. So although stars do have a z component perpendicular to the disk, which is non-zero, velocity in the z direction is very much smaller than the velocity in the plane of the disk, and therefore to first approximation you can ignore it. Okay, and we just work with VR. So the acceleration of the star moving in a circular orbit just needs to be balanced by the gravitational force. And so the force on a unit mass is given like this, v square r over r. And to calculate the force, we need to sum up all the gravitational force from the bulge, disk, and halo. And if we do that, somehow we measure how much mass is contained within the radius r, and we denote that by mr, then the gravitational force will just be gmr by r square. And we are going to observe VR, and we of course know R. We can measure MR. That is how the velocities, how the masses of within a certain radius are measured. And this of course will give you the total mass, including the dark matter, etc. So you can then compare it with the visible baryonic mass. To calculate the baryonic mass, you will measure somehow the mass in the stars, you will measure the mass in the gas, you will measure the mass in the dust, you will add it all up to get the total baryonic mass. And then you can compare it with this gravitationally measured MR and see how much dark matter there is. If you have a pure thin exponential disk, which means there is no bulge, okay, then the calculation of this MR, see, remember here there's no integral that we are solving to get MR, etc. We're actually trying to calculate MR, okay, from the VR, right? But suppose you know that it's a special case. A pure thin exponential disk is one example. Then you can write the circular velocity square as the r times the radial gradient of the potential, right? Solving this differential equation will result in a solution that includes modified Bessel functions of the first and second kind. If you do some algebra and section 2.6 of Binney and Tremaine and a few of the sections following that, contain a detailed discussion of this calculation. And then you will get an expression for VC square of R as a function of the mass of the disk, the radius of the disk, and so on. This kind of rotation curve has a peak at Rmax of 2.2 RD, and for R greater than 3 times the maximum, the curve is Keplerian, nearly Keplerian. And so this is what you expect to see, that out at the highest radii, far outside the galaxy, it should become Keplerian. And what you would see. Now, of course, this is a very idealized case. The pure thin exponential disk does not exist in the real universe, but it's useful to do this calculation because you can then compare what the ideal situation should be and what it actually is. This is what it actually is. So this is a measure of the rotation curve of the Milky Way going fairly far out. Okay, so this is out to 10, 12 kpc, and there are measurements going further and further out to 16, 17, 20 kpc, etc. In the outer reaches, it becomes easier to measure the velocities using gas, okay, the kinematics of the gas. So you do it with a radio telescope, measure the H1 velocities, and use that to trace the rotation of the galaxy. Sorry? Yes, no, yeah, it's the radius of the disk. Yes, usually just the optical part, the stars, right? The Milky Way rotation curve. So this is from an old textbook. So it's relatively dated. Now we have much better measurements of the rotation curve of the Milky Way, but the broad characteristics are still there. There is a rapid rise near the center, then there is a fall off, and then it remains flat, but it's not completely flat. It goes up and down. There are large scale structures there in the Milky Way. And now with Gaia, we actually will be able to measure this very, very accurately because we are actually measuring the positions of individual stars. We are measuring their velocities, and we can construct the gravitational potential at any point in the galaxy pretty accurately now. And using that, we can calculate the rotation curve. So now with Gaia, we are basically going from here to here. We are using the MR that we have to predict the VR, and we are comparing the observed VR with the predicted VR, and inferring not just the distribution of the baryonic matter, but also the distribution of the dark matter, because these two will be different depending on whether you do it, whether you use velocities to calculate mass or mass to calculate velocities. Okay, so a few times in these lectures, we mentioned the stellar halo. So just a few words about that. So the Milky Way and M31 have resolved halos with metal poor stars and some globular clusters. Both of these systems contain significant substructure from tidally stripped dwarf galaxies and globular clusters. However, M33, which is the third big galaxy in the local group, although significantly smaller than both Milky Way and Andromeda, does not have a significant stellar halo. detecting a stellar halo observationally is not possible for more distant galaxies because it's very faint, and because the number density of stars is very, very low. And so you can't detect it. So you can't go to even redshift 0.1 and say that, okay, does this galaxy have a stellar halo? You can't do it directly, but as we shall see in a minute, you can do it indirectly. So in 2003, Brown et al. Did some very interesting work. So this is an image of the Andromeda galaxy. And what Brown et al. Did is that they pointed the Hubble Space Telescope at this green square that you see. So now this is obviously way outside the disk of the galaxy, way outside the bulge of the galaxy. But the stellar halo does contain stars over there. The stars of the stellar halo are present. And the Hubble Space Telescope allows you to A, image very faint stars, and B, do it at very high resolution so that all the stars are nicely separated. So this is the image that they took. Some of the brighter stars are in the Milky Way, they're nearby, but most of the fainter stars are stars in the stellar halo of the Andromeda galaxy. Okay. And now there were some open questions like how much of the stellar halo is in the form of tidal streams, how many galaxies have stellar halos, and so on. And the first question they could try and answer is that how much is it in the form of tidal streams. So what they found was when they looked at the stars in the stellar halo of Andromeda, they found that about about 50% of the stars were old. They were like 12, 13 billion years old. But about half the stars were only about 6 or 7 gigayears. So there were clearly two populations. And what they were able to show from the metallicity content of the younger stars, where do you think which of them will have higher metallicity, the young stars or the old stars? Huh? Old or young? Why old? Yes, but they don't, you must remember that they don't produce that much metal until they die. Okay. So the sun, for example, is converting hydrogen to helium, but it is not, remember metal means everything except hydrogen to helium, right? So old stars, even low mass old stars are usually low metallicity. It is the young stars, which are often second generation stars, which have formed which just pick up their metals. They don't form metals themselves like the sun, but being second generation stars, they inherit a lot of metals from the interstellar medium from first generation stars that have exploded. So the young stars were actually high metallicity stars. And they were able to show that very likely these are actually stars from the disk of Andromeda that were pulled out tidally because of some close interaction that it had with some galaxy. The other question, how many galaxies have stellar halos? Is it a very common thing, or are Andromeda and Milky Way special in some way? You can try to answer that question by a technique known as stacking. What you do in stacking is that you combine data on multiple galaxies, just put one image of the galaxy on top of each other. So what this work, Zibetti et al. 2003 did was they took 1000 SDSS edge-on spiral galaxies, and then they oriented each spiral galaxy in the same way along the x-axis. They rotated it so that it was along the x-axis, and then they took a median or a mean of all the galaxies together. So now what they were able to show is that these extended contours that you see here correspond to stars in the hill. So if only 1 or 2 galaxies had a stellar halo out of 1000, then it won't show up in these contours, because when you median it, it will go away completely. Even if you take a mean, it will go away. So they were able to measure statistically what is the sort of average number of stars in the stellar halo of spiral galaxies, and that number came out to be reasonably consistent with what is found in the Milky Way and in Andromeda. And the theory seems to be that all massive spiral galaxies do have stellar halos.
Hello, sir.
Yeah.
Sir, in this image, as they stacked the 1000 galaxies, the shape of the 1000 galaxies will not be the same, like distribution of halos. But when they're taking the mean, why this type of
These were all edge-on, so they were all highly elliptical. There were no circular spirals or anything like that. So that is why that inner contour that you see is highly elliptical. That is the, of course, not all of them will be exactly having same ellipticity. So this is sort of some average over the 1000. Yeah.
okay.
Yes. So the expectation is that the old stars formed in situ in the outskirts of the galaxy, but the young stars formed elsewhere and they have just been transported to the stellar halo. Yes. And that is also true of the bulge. For example, the bulge stars, we believe, formed in the bulge. Disk stars formed in the disk. And as we shall see a little bit later, the kinematics of the bulge, disk, stellar halo, etc. is such that it is very hard for them to, they're all in motion, right? They're not sitting still. So it is not very easy for you to take a star from the bulge and put it into the disk because of the nature of its orbit. Similarly, it's not easy for you to take a star from the disk of a spiral galaxy and put it into its bulge. So that is why those broad trends hold. If there were total mixing happening, you wouldn't see the kind of age and metallicity trends that you see. Right now, you see very definite trends that the metallicity of the disk stars is higher. The metallicity of the pulse stars is systematically lower, and so on. The kinematics is more ordered in the disk stars. It's more disordered in the pulse stars. So, okay. So, yeah. Yes, yes. Everything has to be in orbit, okay? Because remember, it feels the gravitational potential. So it cannot, the orbits can be very complicated. They need not even be closed. So they could be some kind of Lissajous figures kind of orbits are very common in the bulge and in the halo, but they're in orbit. Everything is in orbit. Yeah. Outside in the halo, because cooling becomes relatively more efficient. And so what must be happening is that these clumps form so the kind of star formation that happened in the early times is very different from what is happening now. Okay, so we will come when we talk of galaxy formation, you'll see that the kind of star formation that is happening now is fundamentally different from the star formation that happened in the first 3 or 4 billion years of the history of the universe. So when we come to that, I will discuss things like violent relaxation and so on, which will tell you about how stellar orbits changed initially, and whether they and how they formed. And what you're saying is very important and correct, that today if you want to form a star in the galaxy halo, in the stellar halo, you can't. Every single star is either can be brought from outside by some tidal scattering, or it was produced in the halo long time back when the conditions in the halo were very different. Today, if you just want the regular thing, molecular cloud and star formation inside that, that cannot happen in the halo. They don't have giant molecular clouds at all. Today, whatever star formation is happening in the disk, or at least in the high density regions. You can have some star formation in the bulge if there's enough gas, but not in the stellar halo. Okay. So for disk stars, the velocity LOS, so LOS you will encounter very frequently, is the line of sight velocity. Okay. So we measure velocities in different directions, and we measure the radial component of that velocity, and that is what is called VLOS. And that you will find if you take any patch of the disk, that the VLOS is much larger than the sigma LOS. And that is what we said last time, is that if the standard deviation of the velocities is much smaller than the velocities themselves, that means those velocities are ordered, irrespective of whether the velocities themselves are low or high in value. So stars are kinematically cold and have approximately circular orbits, and usually V stars and V gas are quite comparable. So if I take one patch of the galaxy, of the disk of the galaxy, I measure the speed with which stars are moving there, and then I take a radio telescope and I measure the speed of the gas, I will find that they are quite comparable to each other. Sometimes, however, the star orbital rotation velocity can be slower than the gas. This is referred to as asymmetric drift and indicates a higher stellar dispersion. In S-zeros, you have 30% of objects have what are called counter-rotating gas disks, which means the gas and the stars are not moving. Forget having the same velocity. They're not even moving in roughly the same direction. They are either completely counter-aligned, okay, or they are at least misaligned, which means the velocity vector of the stars and the gas is not 180 degrees, but is at some other angle. How do you think this is possible? Sorry? They don't have arms, then? Yeah, so usually it is more likely that it is gas merger with a low mass gas rich galaxy with its own angular momentum, which falls in. And if it has happened relatively recently, then the angular momentum transfers, etc., nothing happens. So the gas continues rotating the way it is. So obviously after some time it may slow down and start rotating properly. Yeah. Which one? It can happen, but it is much rarer, because in elliptical galaxies, you classify, one of the ways in which you classify an elliptical galaxy is the total lack of gas. Okay, so you probably would relabel it as a S-zero. But there are some star forming blue ellipticals with gas at the center and counter rotating disks and so on. They do exist, but more common in S-zeros. Okay, so when you are studying galaxy rotation, you can study the rotation of the stars. You can study the rotation of the stars and the hydrogen together by observing the gas in the outskirts with a radio telescope. And then you can make a map of the hydrogen velocities. Okay. And so here clearly there is some red shift on the lower side, some blue shift on the upper side. And the contours, if you make contours from the last image, which means you connect all the blue regions and the yellow regions, red regions, etc., you will get what is called as a spider diagram. And this is what it looks like. It's a contour of equal velocity. So the Doppler velocity at every point on a particular contour of the spider diagram is equal. So something is moving at 30, you connect all points moving at 40 kilometers per second, then connect all points moving at 100 kilometers per second. And that will give you the contours which are referred to as spiral diagrams. So this will also tell you which is the blue shift, which is the red shift, and so on. And yeah. No, because one side is red shifted and blue shifted. So this is not the magnitude of the velocity. This is a separate contour for minus 20 kilometers per second and a separate contour for 20 kilometers per second. Okay. So you can think of it, if I go back to the Sauron diagram. So here you will have a contour corresponding to this boundary between, say, red and yellow. So that will be one contour. And then that boundary between yellow and green will be another contour. Then this green and blue will be another contour. So that is why it's yes. Yes. Across what? Across in the Z direction. Yes. Huh. At a certain radius, yes, because that is very small. See, Vz, suppose V goes from 0 kilometers per second to, let's say, 300 kilometers per second. And if your Vz goes from 0 kilometers per second to 5 kilometers per second. Yes. Huh. No, that is very small is what I'm saying. So you can always, these are orthogonal axes. You can decompose the velocity into VR and VZ. What I'm saying is that VZ is so small compared to VR that we ignore it. That's all. So in the spider arm, we can define what is called the kinematic major axis. It is the line through the nucleus perpendicular to the velocity contours. Okay, so here you take something like this, right? That would be your kinematic major axis. Kinematic minor axis is the velocity of line of sight contour at V systematic through the nucleus. Okay, so that is the thing that basically is moving at the same speed as the nucleus. So if a galaxy is rotating like this, there will be a line where things are not moving at all. So that's the kinematic minor axis. The kinematic major axis aligned with the photometric major axis, and kinematic minor axis aligned with the photometric minor axis implies there is a circular velocity in an inclined circular disk. Okay, right? Because that, remember, it's all inherently circular, and the kind photometric minor axis is due to inclination effects alone. Equally spaced contours across the nuclear KMA, kinematic major axis, indicates what? Solid body rotation. Okay, that V is proportional to R kind of thing. Bars often show evidence of radial motion over the bar region. Okay? So if you have a bar in a galaxy, then stars are moving in the bar. They can be moving in the radial direction. It's not circular. It's not in. So the tangential velocity is small, but the radial velocity is very high. If you have a warped disk, then you have twisted contours in the outer parts. So this is like, so this is how you interpret the spiral diagram. Spiral arms yield small perturbations. So how do the spiral arms affect the kinematics of the galaxy as a whole? Does it change the nature of the spiral diagram? The answer is that they yield small perturbations to the line of sight velocities near the arm positions, although photometrically they are large perturbations. So yeah. Completely face on. Yes. So if you are looking at a galaxy completely face on, then all the velocities are sort of perpendicular to your line of sight, and the component in the radial direction is 0. So even if the galaxy is rotating, you won't see it anymore. Yes. So it has to be at least slightly inclined. So there is sufficient radial velocity component. Yeah, you're right. So the thing to remember with spiral arms is that photometrically they're very prominent, but kinematically they are not that prominent. So now people said that, okay, we have these observations, we have spiral diagrams. Nowadays we have even better. We have in place of the spiral diagrams, we have the full 3D IFU spectrum. So they're like high fidelity spiral diagrams. Question is, can we have some kind of modeling, use this to construct the model of the rotation of the stars in the disk? So here you construct, so one of the most popular kind of models are what are called tilted ring models. Okay, so it's not exactly in one plane. The whole thing is slightly tilted. Okay, and you use that model to predict what the spiral diagram will look like. You compare it with the actual spiral diagram, and you modify your model until your predicted spiral diagram matches the real spiral diagram. So these kind of modeling is also done. There are people who do the modeling of the disks. Remember, a lot of the modeling work is focused on the kinematics of the disk because that is simple to understand. It's a circular object with circular velocities, except for the bar, circular velocities dominating. It's basically just V of R. There is no phi dependence. And because these spiral arms, even if they're present, they have such a small perturbation, you can actually construct construct a V of R model of rotation in the galaxy disk without worrying whether that line is going through a spiral arm or not. Right. So these kind of kinematic studies are useful because they can be used to study a number of correlations that characterize the global properties of galaxies. The global properties of galaxies could obviously, luminosity is an important one. What is its size? By size here one means the optical extent of the galaxy. It's measured by some Petrosian radius or some such parameter. Surface brightness. So within the galaxy, how is the light distributed? The rotation velocity as measured with spectroscopy. And the interrelationships between all of these global parameters are what are called scaling relations. And they're important because they reveal something about the internal properties of galaxies, but they must also arise naturally or be predicted by the theories of galaxy formation. In the case of disk galaxies, the most important parameter is between the rotational velocity and the luminosity. Okay, does anyone know what this is called? Tully Fischer relation. Okay, that's absolutely right. So the Tully and Fischer in 1977 recognized that Vmax, which is, we know that for a spiral galaxy, the rotation curve rises and then it is sort of relatively flat for a long time. So that corresponds to Vmax. The maximum rotation speed correlates with the galaxy luminosity. And of course, like most laws in astrophysics, this is also a power law. L is proportional to Vmax raised to alpha. And alpha varies a little bit depending on your sample, but it's mostly between 3 and 4. The scatter in the Tully-Fish relation is smaller at longer wavelengths. Okay, and any idea why this may be true? What will you preferentially see? By longer wavelengths, one doesn't mean radio. One means sort of near infrared. So if you observe a galaxy at near infrared, and dust is less, correct? But you just pick up more. Where will you detect more stars? At longer wavelengths or at shorter wavelengths? Yes, where do they peak? In near infrared or optical? Forget mid there. They peak in near infrared. Okay, so they peak in near infrared, and so you'll be able to sample more stars in the disk when you observe it at near infrared. That the disk is brighter at near infrared than it is at optical, except for the spiral arms, of course, which are much fainter. But the disk as a whole is brighter, and so you get essentially higher signal to noise data, and then your scatter in the Tully-Fischer relationship becomes smaller, indicating that the scatter in the first place was not due to was entirely due to, or mostly due to, measurement errors, not to any systematic or real scatter in the relationship. Okay, the Tully-Fischer relation is an important distance indicator. How do you measure distance with the Tully-Fischer?
We can get the luminosity of the galaxy from the line width, and
Yes.
if we know the flux and the luminosity, then we know the distance to the galaxy.
Yeah. So once you calibrate the Tully-Fischer relationship, you can use Vmax, which is a measured quantity, find the luminosity, and flux you measure. Okay. So now there is a problem with the way these spiral arms are present. They lead to what is called as winding. So question is, why do flat rotation curves lead to winding of spiral arms? Winding means the spiral arms have some distance between each other, right? It becomes tighter. They become closer to each other. Huh? Higher velocities where? In the outer region. So what will happen because of that? Is it actually higher? There is more shearing. Okay, that is correct. But how is that related to the flat rotation curve? Huh? Okay, I think you're on the right track, but so what does the flat, suppose it's a solid body rotator, what would it look like? Okay, so look at this. I'm going to show you a little video. Okay, so this is what you expect a stable galaxy to look like, right? And how is this thing rotating? Like a rigid body. Okay, and would this correspond to a real galaxy? No. Why? Because it won't have a flat rotation curve. It will be a continuously increasing rotation. Velocity will be proportional to r for a constant omega, right? But so obviously we don't observe this. If it were like this, there would be no problem. The velocity would be stable. What we observe is this. If you have a flat rotation curve, this is what happens to the spiral arms. Right? So very quickly, within a few rotations, that spiral structure is completely lost. Right? Just 2-3 rotations later, it goes away. So now the question is, how can two sort of contradictory things be reconciled? One is flat rotation curves, and which is observed, okay, and long-lived spiral arms. Okay? And how do we know spiral arms are long-lived? Because we see them. Okay, again the ergodic principle getting applied. Because the fact that you see spiral arms in so many spiral galaxies indicate that they have to be long-lived. If they are short-lived structures, they will just come and go. You will see it in very few galaxies, and you won't see them every day. Okay, so this is the winding of spiral arms problem. Okay. And this is just what we saw in the video. Okay. There is another issue, which is the spiral arms are defined mainly by blue light from hot massive stars. We saw that these are all OB associations and so on, whose lifetime is much less than the galactic rotation period. So shouldn't spiral arms just fade away? So you have spiral arms formed, there's some overdensity, you formed OB stars, but by the time it completes one rotation, that spiral arm should disappear.
I think in the spiral arms, the stars are sort of moving through the spiral arms, and those are, I mean, it just spends a part of its lifetime in the spiral arms, and then those stars can move and new stars can come. In those,
Yes.
those are perturbations in density and something like that.
Yes. Okay. So that is right. We will look at it next time. But there is one more observation. For galaxies where the galactic rotation has been measured, separately for the spiral arms and for the underlying disk, the spiral arms almost always trail the rotation of the underlying disk. Okay, so the disk is rotating faster and the spiral arms are rotating slower. Relative to the disk, they seem to be rotating in a direction opposite to the disk. Disk is moving in some way, spiral arms. They're also moving in that same, but only relative to the disk, they're moving in the opposite direction, right? So all of these things can be reconciled with a model of for the formation of spiral arms, which we'll look at later. It won't wind, but it'll still wind because you have a flat rotation curve. Okay, you will still end up with winding, except if you drop one more assumption which we have made, which is that the stars in the spiral arms forever remain in the spiral arms. If you drop that assumption, then you can explain all of this quite nicely. So we'll look at that in the next lecture. Okay, so I'll stop now and take questions. Yeah, go ahead. Correct. Along Z axis, yeah. On average, they have the same velocities, but the stars are not necessarily sitting in the central plane all the time. Okay, so they have you know this heard of this epicycles concept, right? Which Ptolemy used to say that okay, there are things in smaller circles and so on. So there are epicyclic orbits. So the stars are in circular orbit, but they do go up and down in the plane of the disk. So they don't stay. A star which is on the central plane does not stay on the central plane forever. It will go above it, then slowly drift downwards, go above it, and so on. Right? So our sun is also doing that. The sun has a z component to the velocity, which varies with time. So it is therefore on an average they are moving at the same speed in the z direction, but because stars are all moving up and down in that. But don't ever assume that again the same star, if a star is in the central plane, it will remain in central plane, and a star which is 100 parsec above it will remain 100 parsec from the central plane at all times. For that epicycle, it is smaller than the full rotation period. So at the radius of the sun, the time taken for one rotation, for the sun to complete one rotation around the central Milky Way, center of the Milky Way, is about 200 million years. And I think it will go 5 or 10 times up and down in that period. So 20, 30, I don't know how much it is exactly. So the epicyclic period is much smaller than the galactic rotation. Now with Gaia, okay. Now with Gaia, we know everything. But previously with simulations, okay, you put in a gravitational potential. You put things in as when you put in the initial conditions, you make sure that it is not completely like Z component is 0 for all stars. You don't do that. You give them some Z component, and then you see how they evolve with time. And everywhere it's basically just solutions of Poisson equation. You calculate the position at t equal to t naught of every star, use that to calculate the gravitational potential. Then you use the gradient of the gravitational potential to calculate the force that each star will feel, evolve it in time at some t naught plus delta. Then you will get new positions for the stars, recompute the potential, and recompute the forces and repeat. So this is how it's done. So in simulations, we know that. But now with Gaia, we really know. We really know for each star how it is moving up, down, left, right. Yeah. We can actually now track things in X, Y, Z or our theta, phi coordinate system. Yes, it could do that for a few nearby galaxies, but it's not going to go that much fainter than HST. HST also, even for Andromeda, it had to do many hours of integration. With JWST, maybe you can do it for a galaxy that is, say, 10 times further away. But even that is just less than 10 megaparsec, which is nothing. Can't Virgo cluster is 16 megaparsecs. We can't hit Virgo cluster also, and that's all nearby universe. So it won't do very dramatically different, but it'll do better than HST for two reasons. One, it's a bigger telescope, and two, it's observing in the near infrared, and these are low mass evolved stars. They are quite bright. They are at their brightest in near infrared. So it will have some advantage, but not that much.